All right, this is section 3.5 for business calculus, and we're still on optimization. And this time we're going to focus in on lot size and harvest size. So these are two important applications of optimization. One is economic, while the other one is ecological. So the first concerns the most efficient way for a business to order merchandise or for a manufacturer to produce merchandise. And the second concerns the preservation of animal populations that are harvested by people. Either of these applications may be read independently of the other. So, for a business encounters two kinds of cost in maintaining inventory. Your storage cost, whether that's warehouse and insurance costs for merchandise not yet sold, and reorder cost, which is the delivery and bookkeeping cost for each order. So for example, if a furniture store expects to sell 250 sofas in a year, it could order all 250 at once, which would incur high storage cost, or it could order them in many small lots, say 50 orders of 5 each, spaced throughout the year, which would incur high reorder cost. So obviously, the best order size or lot size is the one that minimizes the total of storage plus reorder cost. Okay, so we want to minimize our total of storage plus reorder cost. Okay, so that's what we're going to look to minimize. So let's look at the first example. A furniture showroom expects to sell 250 sofas a year. Each sofa costs the store $300, and there is a fixed charge of $500 per order. If it costs $100 to store a sofa for a year, how large should each order be, and how often should orders be placed to minimize those inventory costs? All right, so let's look at storage cost first and think about coming up with that equation. So if the sofas sell steadily throughout the year, and if the store reorders X more whenever the stock runs out, you have a graph that looks like the one below. You order, and then you sell them all till you get to zero, come back up, order more, sell till they get to zero, and you keep that pattern up. Well, the average of that, of what happens normally throughout the year, what they would have on hand, would be X over 2, which means our storage cost, okay, our storage cost is going to be the storage cost per item. And if you look at the last sentence here, it costs $100 to store a sofa for a year. So the cost per item, which is $100 for this case, times the average number of items that we have, which we said was X over 2. So again, those storage cost is going to be the cost storage per item times the average number of items that they have on hand. All right, so in our case, it's going to be 50x. All right, so that's one part of the equation. We need the storage cost. We also need the reorder cost. Okay, so again, those are the two things that we need to do to come up with how to minimize inventory cost altogether. Well, if we read the second sentence, it says each sofa costs the store $300, and there's a fixed charge of $500 per order. So that cost, that reorder cost is going to be the cost per order times, oh no, wrong thing, cost per order. Getting ahead of myself. Would be our $300 per item plus the $500 that we have on hand, or the $500 fixed cost per order. Sorry. So we have two things. We have the storage cost and the cost per order. Now the goal is going to be to minimize that reorder cost, okay, or that cost function. So the reorder cost is going to be the cost per order times our number of orders. Okay? Well, the cost per order is our 300x plus 500. And your reorder number is going to be 250, the total number they expect to sell per year, divided by however many they put in each order. Okay? So that reorder cost is the 300x plus 500 times 250 over x. Okay? And you can simplify that right now or leave it just like it looks. I'm going to leave it alone for now. We'll use it later on in the equation. All right? So, our total cost, our C of x function, this would be the storage cost plus the reorder cost. Is going to be the 50x of our storage cost plus the 300x plus 500 times the 250 over x. Okay? If you simplify this entire equation, we end up with a function, a cost function of 50x plus 75,000 plus 125,000 times x, or times x to the negative 1. Again, this is the function that we want to minimize. So since this is the function that we want to minimize, that we want to minimize, this is the function that we're going to take the derivative of. All right, so I want you to pause the video, take the derivative, and find that minimized value, and then come back and check your work. All right, so if you took the derivative, you should get 50 minus 125,000 x to the negative 2. I rewrote that as 50 minus 125,000 over x squared, and then multiply by x squared on both sides to help simplify the problem a little bit, and solve for x, and we got x is equal to 50. Taking the second derivative, we see that that's always going to be positive, so we do know that x equal to 50 does minimize cost. Okay, so the question actually asked, how large should each order be? So that's our x equal to 50. And then how often should orders be placed to minimize the inventory cost? So to do that, we're going to take 250 and divide by 5. Or not 5, 50, sorry. 250 and divide by 50, which gives us 5. So that means that, so that gives us 5, meaning that we need to have 5 orders, or the lot size is 50, and orders placed 5 times a year. All right, that's the end of example 1. So let's keep going here for a minute. looking at slide 8. So what would happen if that order number of times per year is not a whole number? Okay, in this case, in our example, we had 5, which works fine. You can do 5 orders a year. But what if that had been 7.5 orders per year? All right, what we would do is go ahead and double that to interpret as 15 orders in 2 years. And then over the course of 2 years, you can space out 15 orders. So we made 2 major assumptions in example 1. We assumed that there was a steady demand for sofas and that orders would be placed equally spaced throughout the year. Okay, and that works. That's a reasonable assumption for many products, especially like sofas. But there are seasonal products such as bathing suits and winter coats, and there would be separate calculations that you can do and different data that you can pull in to run these calculations on 2 different times of the year, the on season and the off season. And then you would run it 2 different times and be able to calculate when you should order big amounts in the on season or when you should lay off in the off season. All right, that's the end of part 1.